Hello again and welcome to Section 5, where we will be discussing the properties and behaviors of light. Before we dive into that, let's discuss this really amazing picture here where we're seeing vertical light pillars. Now what's happening here? This is light getting passed through crystals in the atmosphere, little snowflakes as they fall down, and they're deflecting the light, creating these beautiful columns. As usual, let's start off with a relatively simple question. We're going to ask which one of these expressions is the correct relationship between the speed of light, the wavelength of a wave, and the frequency that it oscillates at. Let's go ahead and pause the video, give yourself a moment to pick out your answer, and then come right back. I will argue that you can get this answer purely from unit analysis. What is a wavelength? It is the physical distance you'd measure in meters between a peak to a peak. Sometimes we call them crests. It's equivalent to, say, trough to trough, right? It's just the distance of one oscillation, up and down. Now, frequency, that counts the number of oscillations in a given second. So the unit of frequency would be inverse seconds, which we call hertz. Now, figure out our units. If the speed of light is a distance per time, a meter per second, wavelength's a meter, and a frequency is a oscillations per second, then you're left with A. The speed of light is a wavelength times a frequency. And this equation will come up again and again for us. In this section, we need to build up a comprehensive understanding of light. That means discussing properties like its wave versus its particle nature. What the heck is an electromagnetic spectrum, and how can that help us figure out chemical compositions of things that we'll never physically touch? In connection to all that, we're going to talk about properties that happen to waves and light. Specifically, we'll ask about the Doppler effect, and how that will affect our measurements of what we see here on Earth. And connect this all to the temperature. Every single one of us is glowing in an infrared spectrum now. So what is the relationship between light and temperature? And another one that will matter a lot for us, especially when we talk about stars. What is luminosity versus brightness? Light is our number one tool for studying the universe. Outside of sending objects to our nearest neighbors in the solar system, light is our only method to try and pull out any information. Let's try and put this in perspective. Voyager 1 is currently the furthest man-made object ever. And if we had aimed Voyager 1 at Proxima Centauri, our nearest stellar neighbor, going at the speeds for the time it's moving at now, it would take Voyager 1 75,000 years just to reach Proxima Centauri. And that's our nearest stellar neighbor. And we have an entire galaxy inside just a big chunk of the universe. So it's not practical to try and study the universe by going there. Well, we'd absolutely love to, but we need other tools, other methods to comprehend the universe. And that leaves us with just the properties of light. Now, it turns out, with that, we can learn a lot of things. Temperature, what it's made out of, how fast things are going, and so much more. Understanding the properties of light is a crucial understanding of the universe. The more we understand about light, the more we can understand the universe. So if understanding properties of light helps us understand the universe most, let's talk about easy properties, like the speed of light. How do you measure that? Can you exactly jump in the Millennium Falcon and go for a ride and race along with it? No, that's not possible. So how do you measure the fastest moving thing in the universe? I'd love to hear your ideas. Definitely send me messages, leave comments, anything. I'd love to hear your ideas of how can we measure the speeds of lights. But let's go ahead and talk about what people have done throughout history. In the early 17th century, 1629, a man named Isaac Beekman, he had this phenomenal idea. It involves literally explosives. He had a canyon, and what he did is he set up 2 obstacle tracks. Right? And what he asks observers to do is to sit in a nice safe bunker where the bomb won't hurt them. And he asks them, well, how much time takes between you seeing the explosion in mirror 1 versus mirror 2? Here's the rationale. Take this optical system. Look how long this path is. The speed of light's finite. It doesn't travel instantaneously. And this path is shorter than this path. Therefore, the light going around this shorter path must take less time to reach the observer. So with that, Beekman concluded that all he has to do is get someone to say, look in this mirror, see the explosion happen, and then tell Beekman how much time elapses before they see the explosion in the second mirror. And in principle, this would work. However, his results weren't conclusive, trying to trust humans in measuring what are fractions of a second in difference in time. No dice. But you can improve on this. This concept's valid. You just need bigger distances. A few years after Beekman, the Danish astronomer Romer came around and said, I'm going to use the planets and their moons to measure the speed of light. And this was Romer's greatest insight. He said, look at Io, a moon of Jupiter, as it orbits around Jupiter, and see how long it takes for Io to get eclipsed, to fall into the shade of Jupiter. Well, you'd measure how much time, how long does it take for you to see Io go out of your field of view. And when the Earth is over here, there is this distance between Jupiter and Io that's about 32.9 light minutes. And then here's the key insight by this astronomer. Wait about 6 months. Wait until Earth has orbited around the sun and it's down here. At this point, you've added approximately 2 astronomical units between this distance to Jupiter and this one. In our picture here, I'll say it's closer to 47.8 light minutes now. Look at these differences. How long does it take light to reach Earth from the sun? Right? Light wave coming here reaches Earth in about 8 minutes. Romer has effectively added 16 minutes to this process. He is trying to see how long it takes for Io to go outside of the field of view. There's about 16 more minutes to that measurement. So if Romer knows these distances here, and he measures the time for Io to come out of view, he can measure the speed of light. Absolutely brilliant result. He got a value that was closer to about 2.2 times 10 to the 8th meters per second, which is not too bad. The actual value we know is 3 times 10 to the 8th meters per second. So he was off by about 25%, but he was definitely in the right track trying to measure that speed of light. Now, a modern day measurement of the speed of light can actually be done on a tabletop experiment. Very simple. All you do is you take a laser, and you send it through what's called a beam splitter. Right? Part of the beam will go down to one mirror. The other part of the beam will go to a second mirror. Then you do is you travel this beam and recombine them. Both beams will split up, reconverge, and intersect on the screen where you were making your observations. Right? You control the distances between your beam splitter and the mirrors. That's what this L2 and L1 means. Just the distance, how far that light travels. And using the wave properties of the light, you'll get what's called interference patterns that you see on the screen. And by measuring those interference patterns, you can infer things such as the frequency, the wavelength, and ultimately that speed of the light.